Hello everyone. I'm honored to have the chance to present my paper. I come from Harbin Institute of Technology, Shenzhen, in China. The title of my presentation is Fine-Grade Vulnerability Detection via Conditional Diffusion Probabilistic Models. There are four main aspects to this topic, starting from the research background. Then I'll introduce our proposed methods, and next, I'd like to show the results of our experiments. Finally, I'll introduce our future research directions. Firstly, we will come to the background section. So what are vulnerabilities? Vulnerabilities are security flaws resulting from errors in software design, development, or configuration. Vulnerabilities always be exploited by attackers to carry out malicious actions. In recent years, researchers have proposed many automatic vulnerability detection methods. These methods can be divided into four groups. They are symbolic execution-based methods, rule-based methods, code similarity-based methods, and deep learning-based methods. Many studies have already demonstrated that deep learning-based methods outperform other traditional methods. However, deep learning-based methods still have some limitations. On one hand, the program semantics have not been fully leveraged. Some approaches convert source code into token sequence. However, compared to natural language, source code contains rich structural information. Therefore, these approaches cannot achieve good performance. Other works transform functions into graph-based representations, such as AST, CFG, PDG. But these methods lack interprocedural analysis for source code. On the other hand, the detection granularity is coarse-grained. The granularity of existing deep learning-based approaches is mostly at the function level or slice level. As shown in this figure, we find that the vulnerability involves only a few statements. Thus, it is important to devise a more fine-grained detection approach. Therefore, the aim of our study is to extract more comprehensive and precise semantics and devise a fine-grained detection model. To this end, we first combine control flow, data flow, function calls, and code sequence to construct code-joint graphs, that's CJG, and then, inspired by the application of diffusion probabilistic models in a molecular structure prediction task, we attempt to apply the diffusion model in vulnerability detection. It can achieve fine-grained detection by node classification. Okay, now I will introduce our methods. This figure shows the overview of our FVD-DPM. As shown in this figure, FVD-DPM extracts graph-based vulnerability candidate slices, that's GIVCS, and introduces a conditional diffusion probabilistic model for detecting vulnerabilities. The framework consists of two stages. First, feature extraction. We generate CGG from source code and utilize program slicing technology to extract GIVCS from the CGG. Second, diffusion-based vulnerability prediction. We construct a conditional DPM model to predict lot label distribution for GIVCS. Next, I will provide a detailed introduction to each part of our methods. In the stage of feature extraction, we first combine CFG, DFG, CG, and the code sequence to generate CGG. It not only captures the dependencies among statements within and between functions, but also captures the natural order of the source code. Then we extract SNICE entry loads from the CGG in order to perform program SNICE. Through analysis of many vulnerable codes, we observe that the majority of vulnerabilities are related to API, library function calls, array and pointer variables, and arithmetic expressions. Thus, we select SNICE entry nodes by matching these three types of characteristics. After selecting the SNICE entry nodes, we extract a GIVCS from the CGG. Specifically, starting from the SNICE entry node, we iteratively perform forward and backward slicing until all nodes in the CGG are traversed. Finally, all reachable nodes are collected based on their age to generate the GIVCS. The GIVCS is essentially a subgraph of the CGG. This figure presents an example of the process of generating program slices. Next, we convert all nodes in the graph into low-dimensional vectors to obtain acceptable inputs for deep learning models. We obtain the embedded representations of nodes by combining node types and node values to train a word-to-vec model. The second stage of our method is diffusion-based vulnerability prediction. As shown in this figure, the training process of FVD-DPM comprises two sub-processes, forward diffusion and reverse diffusion. Forward diffusion gradually injects Gaussian noise into the node labels until converging to the standard Gaussian distribution. In contrast, reverse diffusion entails progressively denoising from the standard Gaussian distribution conditioned on the graph structure of GIVCS. Then reconstruct the node labels. We employ GAT to learn the abstract features of GIVCS. In this slide, we give the specific definitions and formulas of the forward diffusion process and conditional reverse process. Gaussian noise is continuously injected into the node label distribution during the forward diffusion process, which is essentially a Markov process. The reverse diffusion process is a conditional probabilistic diffusion process, which learns to reconstruct the forward diffusion process. It is also a Markov process. Then, we improve the diffusion model by simultaneously learning the mean and the variance of the denoising distribution. Moreover, we propose a hybrid time encoding by combining the relative time encoding and the absolute time encoding in order to make the GAT model remember the noise level at each time step. Next, I will show the results to evaluate FVD-DPM. We answer these four research questions. In this slide, we present our dataset metrics and baselines. Our dataset can be divided into two groups. Our group contains two well-known datasets, NVD and SARD. The other groups contain the three real-world open-source projects. They were manually collected from the GitHub. As for baselines, we compare FVD-DPM with 9 state-of-the-art detection methods. This slide shows the experimental results for RQ1. From these tables and figures, we can draw the conclusion that FVD-DPM achieves better or competitive performance when compared to existing state-of-the-art detection methods. Next, we investigate the contributions of different edge types in code joint graph. As shown in this table, overall, the model's performance gradually improved as we added different types of edges to the CFG. Then we evaluate the effectiveness of the hybrid time encoding and the improved training objective. We conduct two groups of comparative experiments. The results show that these improvements help the model to achieve better detection performance. Finally, for answering RQ4, we evaluate the performance of FVD-DPM in locating different types of vulnerabilities. Finally, I will introduce our future research directions. Although our methods can facilitate security experts to analyze the vulnerability more clearly and repair it. However, our deep learning-based methods still cannot explain model decision results. So in future research, we will focus on addressing this problem. In addition, large language models with their powerful generalization ability demonstrate good performance on many code generation tasks, but their performance in fine-grained vulnerability detection is not yet employed. Therefore, in the future, we will explore ways to improve its performance by combining large language models with traditional detection techniques. That is all of my presentation. If you have any questions, I'd be very happy to answer them. Thank you for your attention.